Have you ever felt time slow down on a long drive, then snap back when you arrive? Physics says that feeling isn't just in your head. At high speeds, clocks actually tick differently. Distances squish. Gravity bends the schedule of the universe itself. That's special, and general relativity everyday rules, quietly broken at extremes. Zoom in further and the story gets stranger. Photons act like waves and particles. Choices made now seem to echo backward, and entangled pairs share information in ways that look faster than light. Think of time as a fourth direction. Move more through space, and you move less through time. Simple idea, wild consequences. If this kind of calm, careful curiosity fits your pace, a quick like and subscribe helps others find it. Settle in, everything you know about time is about to shift. Imagine pushing faster and faster until your speed is close to the speed of light. The world would not stay familiar. Shapes would not hold steady. Clocks would not agree. The rules that feel solid at walking or driving speeds would begin to bend. Reaching the speed of light itself is off limits for anything with mass. Only massless particles like photons move exactly at that speed. The reason is energy. To push an object with mass closer to light speed, you must feed it more and more energy, and the curve climbs so sharply that the required energy goes toward infinity. That wall is real, yet nature gives us hints near that wall. In particle accelerators and in showers of particles from space, we have measured bits of matter flying at 99% of light speed, and sometimes even closer. These events tell us what the edges look like, even if we cannot cross them in a spaceship. For everyday life, people will not reach those speeds. Planes and rockets are slow compared to light. Still, it helps to imagine what you would see if somehow you could move that fast. The changes would not be subtle. Space and time would not behave the way you expect from common sense. To make this easier to picture, think about a simple simulation. There is a small research game made at MIT called A Slower Speed of Light. It lets you walk through a virtual world while the program gradually lowers the speed of light in that world. You are not actually speeding up. You keep walking at the same pace. Instead, the speed limit of light is being turned down step by step until it is as slow as a casual stroll. This trick lets you feel what it would look like if you were moving extremely fast in our real universe, because the visual effects depend on the ratio between your speed and the speed of light. At first, everything looks ordinary. Trees, buildings, the ground colors sit where they should. Then the first clear change appears. Color shifts. This comes from the relativistic Doppler effect. In daily life, you notice a Doppler shift with sound. The pitch of a siren rises as it comes toward you and falls as it goes away. Light also shifts, but not in pitch. It shifts in wavelength. Visible light is only a small slice of the full spectrum. Long wavelengths look red. Short wavelengths look violet. Beyond red is infrared heat you can feel but not see. Beyond violet is ultraviolet light that can make some materials glow, and that can burn skin. When your speed is low, these outside bands stay outside your vision. When your speed grows large, the story changes. Because of the Doppler effect, light from objects in front of you gets compressed toward shorter wavelengths. Infrared can shift into red, red toward blue, and ultraviolet may move into the visible band as well. Light from objects behind you gets stretched toward longer wavelengths, pushing visible colors toward infrared. The palette of the world tilts. The result is gentle but strange. Warm roofs and roads ahead can become faintly visible as color where your eyes would normally see only gray. Fluorescent marks in minerals that glow under ultraviolet might show up without a lamp because the ultraviolet shifts into the visible for you. At the same time, colors behind you can wash out and slide toward dull reds or even fade beyond sight. This is not magic. It is the same physics as the siren's changing pitch, applied to light and amplified by extreme speed. The name relativistic Doppler effect simply means the usual Doppler idea, plus the extra factors that appear when speeds are a big fraction of light speed. Another effect adds to the mood. Light is both a wave and a stream of particles called photons. When you move into a headwind of photons, more of them strike your eyes per second from the direction you are facing. The view ahead gets brighter and sharper. When you look behind, fewer photons reach you from that direction. The view dims and thins. This focusing of light into a bright, forward cone is often called the searchlight effect. It makes the path in front glow while the path behind falls into shadow. The world seems to recenter itself toward where you are going. If you play the MIT game, you may have a second feeling that seems odd. Even though your walking pace does not change, you begin to sense that you are covering ground faster and faster. As the simulated speed of light drops, it feels like your body has sped up. The code tells another story. Your speed is the same. Instead, time and space in the simulation are changing relative to you. This points to the heart of special relativity. In our universe, the speed of light in empty space is constant. That number never changes, no matter how you move or where you are. Because that speed is fixed, time and space must be flexible. They adjust themselves so that every observer, whether standing still or racing fast, always measures the same light speed. The adjustments are not a mistake in the instruments. They are built into reality. Time dilation is one of those adjustments. The phrase sounds heavy, but the idea is simple. A moving clock ticks more slowly compared to a clock at rest, as judged by the rest clock. If you send two identical clocks on two paths, one stays on Earth, one rides a rapid rocket, and you bring them back together, they will not show the same time. The traveling clock will have counted fewer seconds. This is not a theory in the casual sense. It has been tested many times. Tiny clocks flown on planes return with measurable differences. Particles that usually decay in microseconds live longer when they are moving fast because their internal clocks are slowed. Even satellites that make GPS work must include time corrections. Their clocks tick at slightly different rates because of both their speed and the gravity they feel. The change is small, a few milliseconds per year when you add the effects up carefully. But if you ignore it, your map would drift and your phone would miss the mark. Over days and months, those milliseconds matter. Another linked effect waits beside time dilation: length contraction. The phrase means that from your point of view while moving fast, distances in the direction of your motion become shorter than what a stationary observer would measure. You do not feel squished. Your ruler and your body feel normal to you. But when you compare notes with someone at rest, you disagree about how long the road was. Their clocks and rulers match their frame. Yours match yours. Both are right inside their own frames. And that is the key to staying calm with these ideas. Back to the simulation. Recall that your walking speed is unchanged, yet near the end you seem to close distances quickly. The pictures above explain it. If your personal time runs slow compared with the world you move through, and if measured lengths ahead shrink in your direction of travel, then from your point of view you can reach far places in less of your own time. In the game, this shows up as a growing sense of speed, even though the code keeps your steps steady. In the real universe, if a spacecraft could cruise at a speed very near the speed of light, the crew would feel normal. Their hearts would beat at a normal rate. Their clocks would tick at a normal pace on board. But compared with Earth clocks, their time would pass more slowly. A trip that takes them 1 year by their clock might match 10 years on Earth if their speed were high enough. The exact number depends on how close to light speed they travel. These facts can lead to a tempting thought. If time slows enough, could a traveler reach a distant star in no time? At the exact speed of light, time for a photon does not advance at all in that special sense. A photon does not age between its birth and its arrival, but a photon is massless and a person is not. For anything with mass, reaching the exact speed of light is not possible. The energy wall blocks the way. Still, it is useful to carry the thought as a limit. If you could somehow ride exactly at light speed, every journey would take 0 of your own seconds, while the outside world would still count years equal to the distance in light years. Go to a star 40 light years away at light speed, and people on Earth would see you arrive 40 years later, even though you would not have felt the weight. That is the sharp edge of the idea. In practice, travelers with mass can only approach the limit, not touch it. The closer you get, the stronger time dilation and length contraction become, and the more dramatic the split grows between your experience and the records kept by those who stay home. There is one more visual twist to add, and it often surprises people the first time they hear it. The scene in front of you would not only shift in color and brightness, it would also seem to squeeze toward the direction you are heading. Lines that were straight may bend. Objects from the side may appear to slide forward into your view. This change in what fits inside your field of vision comes from 2 linked ideas: aberration of light and the Lorentz transformation. Aberration, in simple terms, is how the apparent direction of incoming light changes because you are moving. You already know a mild version from rain. If you walk in still rain, the drops seem to slant toward your face even when they fall straight down. Light does something similar at high speed. Rays that would have reached you from the side get tilted toward the forward direction. The circle of the sky in front tightens. More of the world crowds into that circle. The Lorentz transformation is the mathematical rulebook that ties all these changes together: time dilation, length contraction, and aberration, so that the speed of light stays the same for everyone. Because light takes time to travel, there is also a built-in delay between an event and your seeing it. You never see a thing at the exact instant it happens. You always see it as it was. At normal speeds and human distances, the delay is so small that we treat it as 0. At high speeds or across large distances, it becomes obvious. Even in the quiet setting of a screen and a chair, there is a tiny delay. Photons leave the pixels, cross the short gap, and then meet your eyes. That gap is small, but it is not nothing. You are always looking a little bit into the past, even here, even now, as light takes time to leave your screen and reach your eyes. When light is no longer instant enough, the place you think an object sits and the place it really is will drift apart. In the slowed light world of the simulation, that drift shows up as clumsy turns and late reactions. It looks like poor control. It is really delayed information. As the game lowers the speed of light with each orb, every wall and corner you see is the version from a moment ago. By the time those photons reach your eyes, both you and the scene have moved. So you begin a turn where you would turn in ordinary life and still clip the edge. To stay safe, you have to start steering earlier than feels natural. It is the same feeling as playing with network lag. Your hands are on time, the picture is late. This delay changes more than timing. It also changes what fits inside your view. The direction a beam of light points when it leaves a source and the direction you must look to catch it are not the same when you are moving fast. The animation in the simulation makes this clear. As you walk forward, light that left a lamp from the side still needs a little while to reach you, during which you have walked closer to the direction of its travel. The ray seems to slide forward in your view. Many rays do this at once. The circle in front of you tightens and gathers more of the world, like a wide-angle lens appearing out of nowhere. This growth in effective field of view is a mix of aberration, which is the change in apparent direction of incoming light for a moving observer, and plane travel time delay. Once you stack delays on top of color, shifts, and brightness cones, light, space, and time begin to braid together. The picture gets busy. The simulation keeps the focus simple on purpose. It does not try to model the full tangle you would meet if the real world's light were truly slow. In reality, Earth is already moving around the sun around the galaxy, and light bounces inside circuits that run your cameras, screens, and radios. Slowing light in that world would ripple through every system we build. Clocks would drift, electronics would fail, navigation would be hard. The game leaves those complications aside so you can feel the core ideas with calm clarity. Thinking in the other direction is useful. If a traveler could approach light speed, instead of bringing light down toward walking speed, long trips would compress in the traveler's own time. That does not make all problems go away. For people back home, time keeps a normal pace. You leave, you age slowly, you return, and many years have passed on Earth. The gap can be years, centuries, or more, depending on how close to light speed you cruise and how far you go. Outside the ship, the scene would not only age faster relative to you, it would also look warped. Aberration would pull the sides forward. The band of visible colors would widen in front as infrared and ultraviolet shift into view. The forward sky would brighten in a tight cone. Behind you, the world would dim and stretch. The universe would feel organized around your path. These ideas set the stage for a more familiar example: the pace of time on Mercury compared with Earth. At first glance, you can talk about a day on Mercury in the simple sense of how long the planet takes to spin once relative to distant stars. That sidereal rotation period is about 58 days, 15 hours, and 30 minutes of Earth time. Astronomers get this number by watching surface markings, radar echoes, and the way the planet's features line up over many nights. Mercury's year, its orbital period around the sun, is different again, about 88 Earth days. Because the spin and the orbit interact in a 3-to-2 resonance, the length of a solar day on Mercury, noon to noon, is about 176 Earth days. The details of which day you mean remind us that time is measured by processes, and different processes can tell different stories, depending on motion and gravity. The deeper point is that time itself does not run at exactly the same rate everywhere. Speed affects it, gravity affects it. Near the sun, the gravitational field is stronger than on Earth's orbit. In a strong field, clocks tick a little more slowly compared with clocks far away. That is gravitational time dilation. The effect is small for planets, but it is not zero. If you could place two identical atomic clocks, one at Mercury's average distance from the sun and one at Earth's distance, and compare them from far away, the one deeper in the sun's gravity would run a bit slower. The difference would be tiny in everyday terms, yet it is real and measurable with precise instruments. It helps to pause and say what we mean by time in plain words. Time is the way we order events, so they do not all happen at once. It separates before from after. It is the reading on a clock that increases as things change. In daily life, you can think of yourself as always moving through time toward the future at 1 second per second. That line is simple and steady enough to trust for work, sleep, and plans. Einstein's insight was that this steady rate is not the same for all observers once high speed or strong gravity enters the picture. The total speed limit of the universe, light speed, stays the same for everyone. To keep that limit fixed, nature lets the ticks of clocks and the lengths of rulers shift depending on motion and position in a gravitational field. Special relativity describes the role of speed. The faster you move relative to someone else, the slower your clock runs compared with theirs. It is not that your clock is broken. Within your own ship or car, your heartbeats and seconds feel normal. The difference appears only when you compare with someone in a different state of motion. This is why a traveler who spends a long time at high speed ages less than a person who stays home. The rule has been checked with many tests. Subatomic particles that normally decay in a flash live longer when they fly through the atmosphere at high speeds. Atomic clocks flown on aircraft and rockets return with small but solid shifts in their readouts compared with twins that stayed on the ground. The numbers match the equations when you account for both speed and height. General relativity adds gravity to the picture. In that theory, gravity is not a force in the usual sense. It is the shape of space-time. Mass and energy tell space-time how to curve, and curved space-time tells matter and light how to move. A useful way to say it without math is that clocks run a bit slower, deeper in a gravitational well. Deeper means closer to the massive body where the gravitational potential is lower. The sun's well is deeper than Earth's. Earth's is deeper than the height of a satellite. The surface of a mountain is a little less deep than sea level. The change is tiny over human scales, but careful experiments see it. A landmark test came in 1959. In the Pound-Rebka experiment, physicists sent gamma-ray photons from the top of a tall tower to detectors at the bottom. According to general relativity, as light drops deeper into Earth's gravitational field, its frequency should increase by a very small amount by the time it reaches the bottom. That is exactly what they measured. If you like a picture, think of the peaks of the light wave as cars on a highway. As they move into congested space near the bottom of the well, the peaks are closer together, which means the frequency is higher. No cars actually push each other. The geometry changes the spacing. In the lab, this change is extremely small, but measurable with careful methods. These effects are not just curiosities. We rely on them. The timing in the global positioning system is an everyday proof. GPS satellites carry very stable atomic clocks. Those clocks are high above Earth, where gravity is slightly weaker than on the ground, so they tick a bit faster due to general relativity. The satellites also move quickly along their orbits, so their clocks tick a bit slower due to special relativity. Engineers combine both corrections to keep the entire system in step. If they did not, the differences would add up. Positions would be off by several kilometers within a day. The fix is to program the satellites so their timekeeping stays aligned with ground clocks once both speed and gravity are accounted for. Returning to Mercury with this in mind makes the idea clearer. Clocks on or near Mercury sit deeper in the sun's gravitational well than clocks on Earth, so they run a little slower relative to Earth clocks. All else equal, Mercury's own speed in orbit is also higher than Earth's average orbital speed, which adds a small, special relativistic slowdown compared with a clock at rest relative to the Sunday. The combined effect remains small for human senses, but precise enough for instruments and important enough for any future navigation near the planet. When we quote day lengths for Mercury, we are usually talking about how fast the planet rotates or how long the sun takes to return to the same noon position in its sky, measured by Earth clocks. If you stood there with a well-shielded clock and compared notes with someone on Earth, you would agree on the sequence of events, but not on the exact count of seconds that passed between them once all the relativistic factors were folded in. Speed, gravity, and vision also weave together in practical flight. Picture a craft headed inward toward the Sunday. As the crew dives deeper, their clocks slow slightly relative to clocks far away. The light from the sun grows more intense and blue-shifted in their forward view, while the star field behind stretches redward and dims. Radio signals traveling between the ship and a station on Earth take time, and the frequency drift must be corrected for both motion and gravity. Navigation software uses relativity not as a decoration, but as a baseline. The same habits apply in orbit around Earth. Even for low Earth satellites, the net time drift is a blend of altitude, faster ticking, and orbital speed, slower ticking. The right way to keep systems synchronized is to calculate both and adjust. One common question is whether living closer to a massive object could make people live longer. The accurate way to say it is that your biological processes and your clock would both slow by the same tiny factor relative to a far-away observer, so you would not feel extra time inside your own life. You would not gain extra birthdays from your point of view. Someone far away might say fewer of your seconds passed than theirs over the same comparison period. The shift is interesting and real, but it does not change your personal rhythm. All of this returns us to the quiet rule that guides the simulation and the real world alike. Information arrives with delay, and clocks depend on motion and gravity. When the delay is small, you can ignore it and walk as usual. When the delay grows, you must lead your turns and widen your awareness. When the gravitational field is stronger, clocks run a little slower. When a system moves fast, its time stretches relative to a system at rest. Instruments built with these facts in mind work with greater ease. Instruments built as if time were the same everywhere drift. The last point is easy to miss because the corrections are small, but modern life stacks small effects into big systems. A few microseconds per day does not sound like much until you multiply it by thousands of days and billions of device uses. The practical answer is to design with relativity from the start. That is why satellites are programmed with the right offset and models of Earth's gravity and their orbital motion. When they are farther from Earth's gravity, time runs a bit faster for them. When they move quickly, time runs a bit slower. The net effect is the sum of both. Without this correction, their internal clocks would drift from our clocks on Earth, and navigation results would slide away from truth. When the game keeps lowering the speed of light, the place you see an object and the place it actually is stop lining up. That is why the avatar bumps a wall after you think you've cleared it or drifts past an orb you aimed for. It isn't sloppy control, it's delayed information. Each orb slows light in the simulation, so every surface you look at is the version from a moment ago. By the time those photons reach you, both you and the scene have shifted. To avoid a collision, you have to begin your turn earlier than your habits suggest. It feels like playing with network lag. Your hands are on time. The picture is late. This delay also changes what your eyes can gather in one glance. As you move forward, rays that left a lamp off to the side take a finite time to reach you. In that time, you have moved. So those rays arrive from a more forward angle than you expect. Many directions get pushed toward the nose of your motion. The front of your view seems to widen, almost like a lens that slowly goes more and more wide angle. The animation in the demo is a simple way to see it. The source moves relative to you, but because light needs time to reach you, you see where it was. When there is a lot in the scene, this makes it feel like your field of view grows with speed. You are not really seeing more at once. You are seeing more of the world projected into the forward cone. Seeing the past becomes normal in that slowed light world, and light, space, and time start to knot together. The demo keeps the knot from pulling tight. It doesn't layer in real-world complications. Earth already orbits the sun. Electronics depend on signals moving at light speed in glass and copper, and timing holds whole systems together. If light truly behaved this way in daily life, everything from power grids to cameras would need a redesign. The point of the game is gentler. Let you feel, without math, what fast motion does to color, brightness, and apparent direction. There is another angle to the same idea. If you could push a ship near light speed instead of slowing light down, then long distances would look shorter in your own time, even though clocks back home would tick along as usual. From the ship, the starfield would deform. The forward sky would grow brighter and bluer. The rear would dim and redden. More wavelengths would slide into human vision in front. Your effective field of view would squeeze forward and crowd with detail. None of this breaks the rule that your own heartbeats and seconds feel steady. It only changes how your measurements compare with someone far away who keeps a different state of motion. Shift focus, then, to a simple question. Does time run at a different pace on Mercury than it does on Earth? We can talk about a day in different ways. Mercury's sidereal day, the time to spin once relative to distant stars, is about 58 Earth days, 15 hours, and 30 minutes. We learn that by watching surface features with radar and telescopes and tracking how long they take to return to the same orientation. Mercury's year, its orbit around the sun, is about 88 Earth days. Because its spin and orbit lock into a 3-to-2 resonance, the solar day, noon to noon, on Mercury is about 176 Earth days. These numbers are set by motion and geometry. They are not yet about relativity, but they do remind us that time is always measured by some process: a spin, an orbit, a vibration, a clock tick. Now add gravity and speed. Time does not move at exactly the same rate everywhere. The faster you go relative to someone else, the slower your clock runs compared with theirs. And the deeper you sit in a gravitational field, the slower your clock runs compared with one higher up. You never feel this as a drag. Your watch, your breath, your thoughts keep their rhythm. The difference shows up only as a comparison between two places or two paths. That is why a clock high on a mountain runs slightly faster than one at sea level, why a GPS satellite's clock runs faster due to altitude, but slower due to orbital speed, and why you must correct both effects to keep a navigation system honest. People often start by asking what time really does. A calm way to say it is, time orders events so they don't pile on to one instant. You can treat yourself as moving through time toward the future at 1 second per second. Einstein showed that this simple pace is not universal once you compare observers at high speeds or in different gravitational wells. Light's speed is the same for everyone. To keep that fixed, nature allows clocks and rulers to shift with motion and gravity. That is special relativity for speed and general relativity for gravity. These ideas are not guesses. They were tested many times. In one famous experiment, two identical atomic clocks were synchronized. One was flown on an airplane while the other stayed on the ground. When they were brought back together, the airborne clock showed a tiny loss of time, just as relativity predicts. Particles called muons, born in the upper atmosphere, live longer when they rush toward the ground at high speed because their internal clocks tick slower. Gravity shows up in timing too. In 1959, the Pound-Rebka experiment sent gamma rays from the top of a tower to detectors at the bottom. The photons gained a tiny amount of frequency while dropping deeper into Earth's gravitational field. The shift was small, but measurable, and it matched general relativity. Modern satellite systems bake these corrections into their design. Without them, positions would drift by kilometers each day. With that foundation, you can ask the natural follow-up. Is Earth's gravity enough to slow time for us in a measurable way? Yes, the effect is small, but it exists. How much? Einstein gave us a compact formula for the gravitational part. In words, it tells you how much proper time, t0, passes for a clock at a distance, r, from the center of a mass, compared with a reference time, t, measured far from any gravity. The constants in the expression include g, the gravitational constant that sets the strength of gravity, and ch, the speed of light, about 300 million meters per second. You do not need the derivation here. What matters is what each symbol means. M is the mass of the body creating the gravity. R is how far you are from its center. G is fixed by nature, and Ech is the speed limit of the universe. T as a hypothetical faraway time. No such perfect place exists, but it's a clean reference. T0 is the time you are solving for at the place you care about. To build intuition, choose a round comparison. For every 60 seconds that pass on the faraway clock, T, how many seconds pass on Earth's surface? T0. Plug in Earth's mass and radius, keep G and C as their usual values, and compute. The answer is about 59.999996 seconds. That means if the gravity-free clock counts 60 seconds, the Earth's surface clock lags by roughly 4 microseconds. Spread that out. About 6 billion seconds need to pass before those tiny differences add up to 4 whole seconds. 6 billion seconds is on the order of 190 years. In a human lifetime, you would gain only about 2 seconds compared with a truly distant clock. Underwhelming, maybe, but very much in line with what our instruments see. Of course, we are not only in Earth's gravity. The sun's mass also curves space-time where we live. Do the same 60-second exercise using the sun's mass and Earth's average orbital distance. Now, the earthbound clock reports about 59.99994 seconds for each ideal 60. The difference is larger because the sun is massive. Even so, it amounts to roughly 1 lost second every 3 years, or about 24 seconds over a lifetime. This is still small, but it is big enough that engineers include it when they build timing systems that need long-term accuracy. What about Mercury, which sits much closer to the sun? If the sun's gravity is the key, Mercury should show a larger shift. Use the same formula with the sun's mass and Mercury's average distance. For each 60 seconds of faraway time, a clock near Mercury's orbit would show about 59.9999 seconds. That means you need something like 60 million seconds, about 1.9 years, for the difference to grow to a single second. Over a lifetime, That adds up to around 38 seconds. Compared with Earth's 24 seconds, the extra benefit is about 14 seconds. The numbers are still tiny. Perspective matters here. If you lived near Mercury, you would not feel like you were collecting bonus seconds. Your own biology and your clock would both slow by the same factor. From your point of view, your days and years would feel normal. It would be Earth that seems to run a touch faster. Point a telescope toward Earth and keep careful time, and over your life, you would watch about 14 more seconds of Earth's history than you would have if you had lived on Earth. That is real and measurable with stable clocks. It is not a path to extra birthdays. Mercury itself is not friendly. High heat on the day side, deep cold on the night side, a thin exosphere instead of a breathable atmosphere. So even if the time difference were appealing, it would not be a practical trade. And the difference isn't appealing, it is small. The deeper truth is that gravitational time dilation in our solar system is modest because our masses and distances are modest in relativistic terms. The sun is huge to us, but nowhere near dense enough to make time crawl for human observers at planetary distances. To make the effect dramatic, you would need an object many millions of times more massive than the sun packed into a much smaller space. Or you would need to get very close to a compact mass without being destroyed. Objects like that do exist. At the centers of many galaxies sit supermassive black holes, with masses of millions to billions of suns concentrated inside a region so compact that even light cannot escape once it crosses the event horizon. Near such an object, space-time is steeply curved. If you fell toward one and somehow stayed intact, your clock would tick so slowly relative to distant observers that, from their point of view, it would approach a standstill as you neared the horizon. In the extreme limit right at light speed for a massless particle, time does not advance at all. For massive travelers skimming the edge of a supermassive black hole, the pace of time could slow so much that it would approach zero. Near a supermassive black hole, the split between your time and everyone else's becomes dramatic. If you could dive close to the edge and then escape, your onboard clock might count 30 minutes while centuries pass for distant observers. From Earth, a telescope would show you moving in slow motion. Each breath would stretch across days. The closer you skim to the boundary, the event horizon, the slower your clock runs relative to the universe outside. At the very edge, the math says, your passage of time trends towards zero. From far away, you would seem to freeze right above that dark border, your signals climbing to higher and higher wavelengths and fading. What if you cross the border? Our present equations can't tell the full story. They were built for the outside and break down at the horizon and beyond. There are ideas for what happens inside, but they remain ideas. The firm part is outside. Gravity shapes space-time so strongly near a black hole that local time can slow to a crawl compared with the time kept by the rest of the cosmos. That extreme picture often sends us back to a quieter question. What is time exactly? We treat it as obvious in daily life. We schedule, we wait, we remember. Yet we do not touch time the way we touch a chair, and we do not see it the way we see a color. We feel change. We count intervals. We find ourselves pushed along, never backward, always forward, at a steady, personal pace. Because time affects everything we do, it makes sense to ask for a deeper handle on it. Not poetry, but a practical model that explains patterns we can measure. Clocks slowing at high speed, clocks slowing in strong gravity. The way light's fixed speed lets us look into the past with telescopes that catch very old signals. One helpful model treats time as another dimension. This is not a claim about fantasy worlds or parallel universes. It is about the structure we already use to describe locations and motions. In common speech, other dimensions sometimes means alternate realities that are similar to ours. Here, dimension means a direction of measurement and movement that is independent of others. You already know 3 such directions. We call them height, width, and depth, or up-down, left-right, and forward-back. Each pair meets at right angles. Those right angles matter because they keep the directions independent. If you move purely upward, you are not moving forward or sideways at the same time. If you combine motions, you can split the result into clean parts along each axis. 3-dimensional space is the world we live in and trust. We recognize it with our bodies every time we turn, reach, or climb. The independence of the axis lets us build maps, stack boxes, and design rooms. It also lets us locate events by 3 numbers, 1 for each axis. With that base in mind, you can imagine simpler worlds with fewer axes and ask what life would be like there. Strip away one direction and you get a flat world, 2-dimensional space. In that world, all motion happens within a plane. You can go north, south, and east-west, but never up. Strip away another, and you fall to 1-dimensional space, a line. On a line, everything exists to your left or your right. You cannot step over anything. You can only pass through by moving along the line. A wall is not an obstacle you walk around. It is a point you cannot cross unless it lets you pass. A thought experiment makes this vivid. Picture a being that lives on a line. All the world that can ever reach it must be arranged along that single path. Its eyes, if it has them, receive signals only when those signals enter the line. A lamp that sits off the line is invisible. A wide object that would be obvious to us appears as a point when the object's edge crosses the line. The 1D being might notice the point appear, grow, shrink, and vanish as the larger object crosses, but it would never see the full shape. The being cannot look around the point because around does not exist in 1 dimension. Even the idea of behind and in front is just to the left and to the right. This is not a trick. It is the logic of fewer degrees of freedom. With fewer independent directions, less can be seen at once and less can be done. 2-dimensional life is richer, but it still has limits that we do not face. A 2D creature can circle an obstacle, draw shapes, and create rooms with walls that fully enclose areas. But it cannot rise above a maze. It must walk every corridor. It cannot stack boxes. It can only slide them. The key detail is always the same. Dimensions are independent directions of movement and measurement. Each new dimension opens motions that were impossible before. Each lost dimension closes them. This ladder of cases gives us a way to talk about going up rather than down. If you add a new axis that is at a right angle to each of the existing ones, you gain a new degree of freedom. That is easy to imagine when moving from 1D to 2D. Draw a line at a right angle to the first. It is still manageable from 2D to 3D. Draw a line at a right angle to both of the first 2 reaching out of the sheet. But from 3D to 4D, we run into a limit of our bodies. How do you draw a line that is at a right angle to 3 mutually perpendicular axes at once? In our physical space, you cannot. Our world gives us 3 independent spatial directions. There is no room for a 4th spatial direction to be perpendicular to all 3 in the same geometric sense we use for the first 3. That does not mean we cannot reason about a fourth dimension. We simply have to accept that our drawings and models will be projections and analogies. A projection is a lower dimensional shadow of a higher dimensional object. You use projections in everyday life without thinking about them. A photograph is a projection, a three-dimensional scene mapped onto a flat surface. The picture holds real information about the scene. Edges line up, sizes change with perspective, shapes foreshorten, yet many details are lost. You cannot tell from one photo how far a mountain is behind a tree unless other cues help. In the same way, a careful drawing of a cube on paper is a 2D pattern that our brains read as a 3D object. The lines are not actually edges in space. They are signals that trigger our 3D sense. Mathematicians and artists have used this trick to sketch 4D objects into 3D space. The familiar wireframe figure called a tesseract is one example. It is a projection of a 4D hypercube, flattened into something our eyes can scan. The inner and outer cubes, the connecting struts, and the odd scaling are all artifacts of the projection. The structure is mathematically consistent, and it follows rules that mirror how a real 3D cube casts a 2D shadow. Still, many people find that looking at a tesseract shape does not give them a deep feel for four-dimensional space. It raises as many questions as it answers. Where is the outside in 4D space? How do angles behave? How would a 4D being look at us? Those are interesting questions, but a picture alone rarely settles them. For most of us, the projection is a hint, not a full explanation. A clearer approach is to focus on what dimensions do rather than how they look. Dimensions give coordinates to events. They tell us how to separate one location from another and how to describe motion. If we carry that function forward, we can ask if there is a direction, independent of the three spatial ones, along which change happens and which orders events. That is where time enters. We use time as a coordinate every day. To meet someone, we specify not only a place, but also a time. To chart a planet's path, we write down positions as a function of time. To describe a sound wave, we name its frequency, how many cycles per second. Time is not a flavor or a force. It is a parameter that lets us locate an event in a sequence. Because events can be at the same place, but not the same moment, space alone is not enough. We need a separate coordinate to tell before, from, after. Calling time a dimension does not mean it acts exactly like a spatial axis. One obvious difference is our human experience of it. We can move freely in space, forward, back, left, right, up, down, while we feel carried along one way in time. Another difference lies in the physics. The geometry that ties space and time together has a different sign for the time part than for the space parts. A technical detail that keeps cause and effect in order and keeps light's speed fixed. But at a practical level, the analogy is still very useful. It helps explain why speed through space and speed through time trade off in relativity. If your motion through space increases, your motion through time decreases relative to someone who is not moving with you. That is the core behind time dilation and length contraction. Your path through space-time has a fixed budget, and you can spend more of it moving across space or more of it moving along time, but the total stays within the same bound set by the speed of light. The ladder of dimensions also helps with mental pictures. Think back to the 1D being on a line. A 2D observer can step off the line, look down, and see the entire arrangement at once. To the 1D being, parts of the world are hidden until they cross the line. To the 2D being, Nothing in that flat scene is hidden. In the same spirit, a 3D observer like us can look at a 2D maze and map every path in one glance. We do not have to walk the corridors to know the exit. Project that logic upward, and you get a sense of why a higher viewpoint changes what can be known at a glance. We cannot take a 4D view of our 3D world, but we can understand why such a view would collapse hidden interiors into visible surfaces. The point is not to imagine new creatures. It is to practice how projections lose information and how a higher dimension, if it existed to us in the same way, would restore it. Another useful exercise is to revisit perpendicularity. Perpendicular axes stay cleanly separate. When you add a new dimension, you are adding a new way to differ from your neighbors that cannot be reached by sliding along the old axis. In 2D, you cannot cheat and call a diagonal a new dimension. A diagonal is a mix of the old ones. In 3D, you cannot claim a fourth axis by tilting in an odd way. Any tilt can be described by combinations of the original three. That is why 4D space cannot be built inside 3D space with real rods. We can only simulate the behavior with math and picture part of the structure with projections. The perpendicular requirement is the guardrail that keeps the concept clean. Why tie time to this framework? Because the behavior we measure matches the pattern. If time were not a coordinate on the same footing as the spatial ones in some geometry, light could not have the same speed for all observers, and the rules about clocks and rulers would not work out. The fact that moving clocks tick slow, moving lengths contract in the direction of motion, and signals never outrun light all fall into place once you accept that space and time are woven together into space-time, with one time-like axis and three space-like axes. The woven picture explains why spinning a system through high speed changes how much of its motion is along the time axis versus the space axis. It also explains why gravity, which curves space-time, changes the rate at which local clocks tick. In a deep gravitational well, the geometry stretches time intervals compared with faraway regions. It is natural to wonder whether we can build objects that show 4 spatial dimensions directly. We cannot, but we can build machines that detect the consequences of space-time structure. Particle accelerators rely on the same geometry to predict lifetimes and paths. Atomic clocks track tiny shifts when you lift them by a few feet. Telescopes that catch light from distant galaxies rely on the fact that light speed is fixed. So looking far is looking back. None of these tools let us walk along a hidden hallway. They let us measure how time and space act together and confirm that treating time as a dimension is more than a metaphor. So while we cannot draw a perfect fourth spatial axis that is perpendicular to all 3 familiar ones inside our rooms, we can still use dimensional thinking to make sense of time's role. It orders events as cleanly as a new coordinate orders locations. It stays independent of the spatial axes in the way that matters for cause and effect. It interacts with speed and gravity the way the space-time geometry says it should. And there is a simple, constant hint that points to its dimensional nature. It gives every event a unique label that cannot be replaced by spatial coordinates alone. There is some evidence, however, that a 4th direction exists, and we are moving along it right now. Time is the 4th direction. In Einstein's picture, space and time are not separate rooms. They are one connected structure called space-time. A location needs 3 numbers for space and 1 for time, and the 4 work together. If you accept that, it feels natural to say time is a kind of direction. We do not look toward it with our eyes, but we move along it all the same. Without time, Nothing in 3D space would change. Motion would freeze. A swing would hang in one position forever. Time is the ingredient that lets space evolve. Why can't we see this direction like we see left, right, or up, down? A good way to explore that is to compare worlds with fewer dimensions and then build a simple model. Start with ordinary 3D space in your mind. To fit space and time into one picture, we will compress all of 3D space down to a flat sheet, the XX plane, and we will use the vertical axis Z to stand for time. Think of the sheet labeled space and the upward axis labeled time. In this diagram, a person who lives in 3D becomes a little 2D figure sliding on the sheet. When that figure moves upward on the chart, that means time is passing for them. The bottom of the chart is their past. Farther up is their future. Higher means older. In daily life, we do not pick our flow through time. We cannot pause it or back up. In the model, treat that as a steady push upward, like a gentle wind that always carries the 2D figure toward the future. You can't slow it by willpower, but the statement, "we cannot change it at all," is not quite right. Motion through space changes the rate of motion through time. That is one of Einstein's key results. If your speed through space increases, the time you personally experience, measured by your own clock, still feels normal. But compared with a non-moving observer, your time runs more slowly. The diagram can express this with a simple vector, an arrow that shows the direction and size of motion through space-time. Imagine an arrow sticking out from the 2D figure's chest. The arrow always has the same length, set by a universal speed budget. You can aim more of the arrow upward into time or tilt more of it sideways into space, but the total cannot exceed the fixed budget. The fixed budget stands in for the speed of light. Nothing with mass can increase its total space-time arrow beyond that limit. You can only rotate where the arrow points. If the arrow points straight up, the figure is not moving across the sheet. All the motion is through time. That is like sitting still in space. If the figure tips the arrow slightly toward the X direction, some of the budget now goes into space. The figure moves across the sheet, which means they are moving in space, but the upward component of the arrow becomes smaller. They move a little less through time relative to someone who kept their arrow straight up. Tip the arrow even more, and the figure crosses the sheet faster. Tip it all the way into the sheet, perfectly sideways, and the arrow no longer points upward at all. The figure's time component vanishes in the diagram. That is the limiting case that only light can achieve. Light spends the entire budget on motion through space and none on motion through time. That is why, in the equations, a photon does not age between emission and detection. It does not advance in time the way a clock with mass does. At walking or driving speeds, the arrow is still almost straight up. The sideways part is tiny compared with the upward part. That is why everyday objects do not show obvious relativistic effects. Your watch, your heartbeat, and your steps keep their familiar rhythm. To notice a change, you must tilt the arrow a lot close to the limit, and that demands speeds near light speed. There is something subtle and important about the viewpoint. For the 2D figure who tilts and slides across the sheet, nothing feels broken. Their own arrow still seems to point forward in time from their chest. Their personal seconds feel ordinary. Their ruler has its usual length. The weirdness is in the comparison. If they stop and reorient their arrow straight up again, then compare with a friend who never tilted, they find that less time passed for them during the trip. The ambient universe did not slow their inner rhythm. The geometry of space-time simply allocates the travel budget differently when the arrow is tilted. This becomes clearer if you add a second figure. At first, both stand still in space. Their arrows point straight up. Their lines in the diagram are straight, rising together. Now let the figure on the right tilt and move quickly along the X direction for a while. Then tilt back and stand still again. The figure on the left never tilts. Later, when they meet, their heights on the time axis are not the same. Less vertical distance has been covered by the traveler. In plain words, the traveler is younger. This is the well-known twin effect in special relativity, shown as simple geometry. No formulas are needed to see the logic. Less upward component during the tilted phase means less total upward progress by the time they reunite. To connect the picture to what each one actually sees, imagine they can project images onto each other's space sheet. The stationary figure watches the traveler accelerate and tilt their arrow sideways. The projection of the traveler's body begins to look strange. A truly flat 2D being turned edge-on would look thinner in the plane. Its shape would seem to compress along the direction of motion. The faster it slides, the more it flattens from that face-on view. When the traveler straightens up again, the projection regains its usual outline, and the age gap becomes plain. The traveler's path used less upward budget. This flattening in the model is not just a drawing trick. It mirrors a real physical effect, length contraction. In Einstein's theory, objects moving at high speed relative to an outside observer appear shorter along the direction of motion. The size across the motion does not change. Only the dimension parallel to the motion contracts. The cause comes from the same trade-off that slows the moving clock. To keep light speed the same for all observers, the rules of space-time force a consistent set of changes. Moving clocks run slow, and moving lengths shrink in the direction of motion. Both effects come from the structure of space-time, not from strain inside the object. The model also helps with why each observer feels normal. The traveler who tilted their arrow never senses that their own ruler shrank or their own clock slowed. In their frame, the arrow from their chest points straight up by definition, because they define the vertical as their personal time direction. Their space sheet is the plane perpendicular to that arrow. Measured on that plane, their ruler is its usual length, and their clock ticks at 1 second per second. Meanwhile, they judge that the stay-at-home person is the one with tilted coordinates during the travel phase. Both descriptions are internally consistent. Only when you bring them back together and compare the full paths their world lines in the diagram does the difference in elapsed time become a single agreed number. If you push the model a little further, it can hold more of the familiar patterns. The speed budget sets the maximum tilt. As you add spatial speed, the time component must drop in just the right way so that the total arrow length stays fixed. That rule gives the standard factor that appears in textbooks, often written with the Greek letter gamma, but you do not need to write it down to grasp the shape. The moral is simple. Big sideways tilt means strong time dilation and strong length contraction. Small tilt means tiny effects. You can also see why no object with mass reaches the limit. To rotate the arrow perfectly into the sheet, you would have to take away the entire upward component. In the physics, that would require infinite energy. You can approach the limit, making the upward part smaller and smaller, but you never zero it out. Light is special because it starts with no mass and always travels with the arrow pointing entirely across the sheet. The picture explains cause and effect as well. The upward axis orders events. If two events cannot be connected by a signal moving at or below the speed budget, They cannot influence each other. The geometry keeps that rule intact no matter how you tilt your coordinates. Slanted arrows do not let you cut across in a way that beats the light limit, because the limit is the shape of the budget itself, not just a posted sign on the road. There is a final visual aid worth keeping. Recall the projection trick from art. A cube drawn on a flat page looks like a cube because of how lines converge and faces foreshorten. The drawing is not a cube, but it carries enough structure that our brain decodes it. The 3D to 2D space-time diagram works the same way. It is not a literal build of 4D reality. It is a projection that preserves the key relationships: independence of directions, fixed total budget, and trade-off between components. When you look at a moving object and you see its length contracted in the direction of motion, you are seeing the real-world echo of that foreshortening rule. When you hear that a moving clock runs slow, you are hearing the time component part of the same rotation. Put the pieces together and the model gives a calm, unified story. Time is a genuine direction in the sense that matters for physics. It is independent of the 3 spatial directions, and motion through space and motion through time share a fixed total budget set by light speed. Tilt more into space, and your progress through time, compared with someone not tilting, reduces. Bring 2 paths back together, and the one that spent time tilted will have aged less. Watch a fast object from the outside, and it will look shorter along its path. Draw it as a 2D figure tipped in a 3D display, and you will see the same flattening appear as a projection effect. This squishing effect happens exactly in line with this model and is to do with time dilation. From the traveler's point of view, nothing about their own body flattens. Their watch keeps its rhythm. Their ruler stays the same length in their hands. It is the outside world that bends. Edges of the scene seem to stretch toward the forward direction. Landmarks at the sides creep into the center. The destination looks farther away along the line of travel, not because the path grew, but because the light reaching the traveler is arriving from shifted angles and shifted colors. A simple 2D model shows only one direction of stretch, but real life is 3D, so the apparent deformation spreads across 2 directions at once. That is exactly what you expect when you tilt your time arrow toward space. The geometry reassigns what counts as a cross and a head, and the image you build from photons reshapes to match. If time truly behaves as a direction, the idea carries weight. It does more than organize drawings. It informs how we think about cause and effect. It also raises calm, practical questions. If there is a steady push that carries us forward in time, what sets it? Why do we never see a local reverse, the way you can walk backward in space? In the diagram, you could tilt an arrow downward, but in reality, we do not witness arrows pointing into a personal past. The model's lesson is gentler. You can tilt your arrow sideways toward motion in space, and that tilt reduces your progress through time compared with someone who does not tilt. The downward option is off the table for macroscopic observers because the rules that keep cause before effect forbid it. The model also suggests an answer to a curious question people sometimes ask. If time is a direction, what is our shape along it? Do we stick out into the future or trail into the past? In this picture, we barely extend at all. We are thin along the time axis, like coins seen edge on. Look face on, and a coin appears round. Turn it, and you see almost no thickness. In the time direction we present that thin edge, you cannot look through time because there is not enough thickness to reveal. The sense of being pushed along rather than spread out explains why you cannot step around a moment the way you can step around a chair. Your form along time is narrow. Your form across space is wide. It is fair to call this a model. It is built to match observations from relativity, not to replace them. What gives it value is how well it echoes the measured effects. Moving clocks do run slow when compared across frames. Moving objects do appear shorter along the direction of motion to an outside observer. Apparent angles of incoming light do swing forward at high speed. In that way, the picture does what a good model should do. It turns a set of equations into a shape you can hold in your head. The same steady attitude helps when we turn to light. Light is not out to deceive us, but its habits are subtle. For a long time, scientists asked whether light was a wave or a particle because it shows features of both. It interferes and diffracts like a wave. It also arrives in discrete packets called photons, which act like particles when they deposit energy. The answer we use today is that light is a quantum field with particle-like and wave-like behavior, depending on how you measure it. That blended nature can feel slippery, especially when you read that observing one way gives you one pattern, and observing another way gives you a different one. One anchor in the middle of this is speed. In a vacuum, light moves at exactly the same speed, about 299,792,458 meters per second for every observer, no matter how fast they are going. That constancy forces space and time to adjust in the ways we have been discussing. Two people gliding through space at different fractions of light speed can both measure the same beam and both get the same answer for its speed. They will disagree about the time between events and the distance between marks, but those differences are what keep the light speed unchanged. It is the geometry doing its job. You may have heard that this neat picture breaks as soon as light enters matter. That is true in a specific, controlled sense. When light travels through air, water, or glass, it does not zip through the material at the vacuum speed. The measured speed of light in the medium is lower. In air, it is only slightly less. In water, it drops to around 225 million meters per second. In common glass, closer to 200 million. The index of refraction is a clean way to summarize this. It tells you by what factor the phase of a light wave slows inside the substance. That sounds like the light itself got tired. The real story is more interesting, and it does not break relativity. Inside matter, the electric field of the light wave pushes on charged particles, mostly electrons. Those electrons cannot fly free in a solid, but they can jiggle in place. When they jiggle, they create their own tiny electromagnetic waves. The original wave and the re-radiated waves overlap and interfere. Sometimes the crests line up and reinforce. Sometimes they offset each other and weaken. The total field is the sum of all of these contributions. The upshot is that inside the material, the pattern that moves forward the wavefront you can track advances more slowly than the vacuum wave would. It is not because individual photons are pausing, taking turns, and then starting again. It is because the medium responds and builds a new wave that, as a whole, has a lower effective speed. You can picture a crowd marching in, step down a street, while residents on porches join in with claps that are a beat behind. The march still moves, but the combined rhythm changes. The marching song that reaches the next corner is not just the original chant, it is the original plus the porch echoes. In optics, the echoes are the induced fields from electron motion, and the song that reaches the far side is the resultant wave. When the wave exits the material into air again, the extra contributions vanish, and the field settles back into the vacuum pattern, which travels at the vacuum speed once more. At no point does information outrun the vacuum speed limit. The way fronts form and move always respects the boundary that space-time sets. You might also hear about cases where light seems to go faster than the vacuum limit, or where a pulse exits a material before it looks like it should. Those cases involve phase velocity and group velocity bookkeeping tools for how waves carry patterns. Phase fronts can move faster than the speed limit without carrying information. In certain media near resonances, the peak of a pulse can shift forward due to reshaping, making it look as if the pulse jumped ahead. In reality, the front edge of the signal, the part that first rises from zero, never beats the vacuum limit. The useful content waits behind that front. What appears faster is a change in shape, not a courier delivering a message quicker than physics allows. The double-slit experiment, where light passes through two narrow openings and draws an interference pattern on a screen, keeps feeding new variations that illustrate these points. In some modern versions, timing and path choices are arranged so that a detector's settings can be changed after the light is already in flight, which tests how measurement affects what we can say about the light's past. These arrangements can be surprising. They can make it feel as though light takes different routes in time and arrives with different apparent speeds, yet still ends up at the same space-time destination. The careful reading is that quantum interference rewrites the pattern of probability. It does not let signals cheat causality, and it does not give photons permission to exceed the vacuum speed. What changes is which histories are allowed to add together and which cancel out. Returning to the ordinary materials we handle every day, the slower march of light in matter is predictable and useful. It is why lenses bend beams. It is why fiber optic cables guide signals. It is why rainbows split into colors, since red and blue experience slightly different slowdowns in glass and water. The details come from how tightly the electrons are bound and how they respond to driving fields. Every substance has its own curve of response across colors. That curve tells you how much delay builds up and how strongly the wave bends when it crosses a boundary. If you write the process out with math, you will see sums and integrals that track all the tiny contributions from the electron's motion. If you prefer plain language, you can keep just 2 sentences. Light's field shakes charges in the medium. The shaken charges radiate new fields that, when added to the original, form a combined wave that advances more slowly and bends according to the medium's index. When the wave leaves the medium, those extra fields go away, and the traveling pattern resumes the vacuum speed, as if the street noise stopped and only the original marching song continued. Scientists have explored and played with these ideas for decades. They have slowed pulses far below the usual speeds in special media. They have created materials whose structure steers waves in unusual ways. They have built devices that delay, store, and release light with exquisite control. All of that rests on the same calm foundation. The vacuum speed of light sets a strict limit in space-time, while materials and interference can reshape, redirect, and slow the patterns we see without breaking that limit. In the late 1990 seconds, researchers found that light's march is not as simple inside special materials as it is in empty space. Using an ultra-cold gas of atoms, cooled to within a tiny fraction of a degree above absolute zero, they created conditions where a laser pulse could be slowed to walking speed, roughly 61 kilometers per hour. A few years later, with the same general technique, they stopped a light pulse entirely inside the cloud, held it for a brief moment, and then released it so it continued on its way. Those results sound dramatic, but they fit within the rules we already have. The key is that what is being slowed or stopped is the pulse, the pattern that carries energy and information, not the fundamental speed limit of space-time and vacuum. Surprises have come from the other direction as well. Around 2000, a different team sent a shaped light pulse through a cloud of atoms and saw something that looks troubling at first glance. The output pulse appeared to leave the medium before the input pulse had fully entered. Taken literally, that would break causality. It would be like walking out a door before your foot crosses the threshold. A careful explanation avoids that paradox. What moved too fast was not the advance of new information. It was the shift of a pulse's peak because the medium reshaped the pulse. Relativity's limit applies to the front of a signal, the very first non-zero rise, and to any transfer of new information. That front never outruns the vacuum speed of light. What can move faster, in some circumstances, is the phase pattern or even the position of a pulse's maximum, and those do not carry fresh content by themselves. To keep the term straight, think about what a photon and a light pulse actually are. A photon is a quantum of the electromagnetic field. When many photons form a short burst, you see a packet with ripples inside. The ripples, the crests and troughs, have a certain spacing, a wavelength that corresponds to color. The pace at which those ripples slide is called the phase velocity. The speed of the packet, the envelope that rises, peaks, and falls, is called the group velocity. There is a third useful idea, the signal or wavefront velocity, which tracks the leading edge where the field first departs from zero. In normal media, phase, group, and front can differ. Only the front is tied to causality in a strict way. A simple picture helps. Imagine a stadium crowd doing a wave. The up-down motion that travels along the seats is like phase. You can watch that ripple race around the arena even though not a single person leaves their chair. The crowd itself, the people sitting and standing, is like the group. If the crowd starts to walk down the aisle while keeping the wave going, the wave pattern might circle the stadium much faster than the people's walking speed, but no message lands at the field until the front row actually arrives. The very first person who steps onto the field is the wavefront. No matter how clever the clapping and swaying, you cannot deliver a note to the coach before that first person reaches the edge. Relativity agrees with that hierarchy. It does not forbid phase velocities above the vacuum speed of light, and it does not forbid strange-looking pulse behavior in media that twist and filter the frequencies. It forbids superluminal transmission of information. In experiments where a pulse seems to jump ahead, careful analysis shows that the medium amplifies the leading part, suppresses the trailing part, and moves the peak forward. The shape changes, so the point labeled maximum shifts, but the front remains bounded by the vacuum limit. There is no message sent faster than light. This difference between how fast the ripples move and how fast a message moves is more than a vocabulary lesson. It matters for the next step. Modern optics can sculpt materials so that their response changes almost instantaneously. When a material's properties are switched on short timescales, the way light interacts with that material can be arranged not only in space, but also in time. That sets the stage for a new twist on a classic test. The classic test is the double-slit experiment. Pass light through two narrow openings, and a pattern of bright and dark fringes appears on a screen. That pattern is a hallmark of interference, where waves line up, crest to crest. The intensity is high. Where a crest meets a trough, they cancel. The same experiment run with single photons, one at a time, builds the same pattern after many trials, showing that each photon's probability distribution interferes with itself when both paths are available. The result reminds us that light sometimes behaves like a wave and sometimes like a particle, and that which behavior you see depends on how you measure. In 2023, a team explored a related idea but swapped space for time. Instead of two slits placed side by side, they created two slits placed one after the other in time. The tool was a thin layer of indium tin oxide, a transparent conductor commonly used in touchscreens. Under normal conditions, a laser beam passes through or reflects with steady behavior. But if you hit the material with a strong, ultra-short controlled pulse, its optical properties can switch for a fleeting moment from transparent to reflective and back again, opening a time window. That window can be only a few femtoseconds long. A femtosecond is a millionth of a billionth. During that window, a probe pulse encounters a reflective surface. Outside it, the surface behaves differently. One switched moment is a single time slit. Send a probe pulse and switch the material once, and you see a clean reflection. With the pulse's spectrum, the spread of its frequencies broadened slightly by the rapid change. That broadening is expected. Abrupt time variations in a medium act like a kind of modulation, mixing frequencies and widening the output distribution. The deeper surprise comes when you create two time slits in succession, switch off, switch, with only femtoseconds between the switches. Now the geometry in space is unchanged. The emitter, the switching layer, and the detector sit in the same positions. The only difference is when the material flips. With two time slits, the measured spectrum shows an interference pattern not in spatial brightness across a screen, but in frequency content. Certain frequency bands dip while others rise, creating evenly spaced notches and peaks. This is the time domain analog of the spatial double-slit fringes. In space, different paths produce different arrival positions and intensities. In time, different switching moments imprint different frequency phases on the same path, and those phases add or cancel when the pulses are analyzed. The fringes show up as missing or enhanced colors within the same beam. To make sense of this on a single diagram, it helps to draw space along a horizontal axis and time along a vertical axis. A probe pulse leaves the source, travels to the switching layer, reflects when the layer is in reflective state, and continues to the detector. Draw that as a diagonal up and right line from source to layer, a kink at the reflection, and a diagonal up and left line to the detector. A second, later probe pulse follows a similar path, but starts higher on the time axis. If nothing odd happened, you would record two spectra that look the same, one recorded a moment after the other. Interference in frequency tells you that something else is at work. For the pattern to appear, the electric field arriving at the detector must be the sum of two contributions with a well-defined phase relation. In the spatial slit case, the two contributions are the two distinct paths through the two openings. In the time slit case, the two contributions are the two distinct moments when the material briefly reflects, each imprinting a different time-dependent phase on the field. The pulses do not need two different locations. They need two different times at which the reflection is allowed. The sum at the detector depends on those time-separated interactions, in much the same way the spatial pattern depends on the space-separated openings. Why does the interference live in frequency rather than in position on a screen? Because varying a medium in time acts like a filter that shifts phase differently across the spectrum. A rapid change multiplies the field by a short-lived gate function. In the frequency domain, that multiplication becomes a convolution, which spreads energy into sidebands. Two gates in time, separated by a small delay, produce a comb-like modulation in frequency, just as two physical slits separated in space produce a comb-like modulation in angle or position. Where the phase difference between the two time interactions equals an odd multiple of pi, the contribution at that frequency cancels and a dip appears. Where it equals an even multiple of pi, it reinforces and a peak appears. The material's quick switch is the time analog of a sharp edge. The two switches play the role of two slits. This perspective connects back to the discussion of phase and group velocities. In a time slit setup, you are not asking a pulse to outrun its own front. You are asking a medium to imprint different phase histories on the same propagating field at two closely spaced instants. The pulse as a whole still respects the vacuum limit when it moves between components. What changes is how the medium's brief reflectivity edits the frequency phases. The detector, which is sensitive to spectrum and phase, sees the edited field as an interference pattern in color space. Nothing in that sequence requires superluminal travel of information. The peculiar look of arriving before entering in other contexts came from pulse reshaping. Here, the peculiarity is a deliberate phase sculpting in time. A helpful way to visualize the time-slit geometry is to imagine the light's oscillations as tilted lines on the space-time diagram. Each crest traces out a slanted line because the field oscillates while the pulse moves. A time slit cuts those lines for a brief interval, reflecting a slice of the oscillations with a definite phase relative to the slice reflected a moment later by the second slit. When the two reflected slices overlap at the detector, some oscillations line up and some oppose, frequency by frequency. The result is a spectral pattern. In the spatial version, path length differences map to bright and dark fringes across position. In the temporal version, time separation maps to bright and dark bands across frequency. You can now see why the experimenters kept the positions fixed. Moving mirrors would have introduced spatial path differences and mixed the effects. By keeping geometry constant and switching only in time, they isolated the temporal interference cleanly. The measured spread and the spacing of the dips tell you the time separation between the slits, just as the spacing of spatial fringes tells you the distance between apertures. Tighten the time gap, and the spectral fringes spread apart. Widen the time gap, and the fringes draw closer together. The math mirrors the familiar formula from the spatial case, with position swapped for frequency and slit separation in space swapped for slit separation in time. There is one more link to make before we move on. Earlier, we treated a photon as a packet with internal waves. That is a simple picture, but it is enough to say something concrete about angles and frequency. In space, if a wavefront arrives at a screen at a steeper angle, the distances between crests projected along the screen become shorter. Shorter projected spacing means higher apparent spatial frequency across the screen. In time, a sudden change in a medium effectively tilts the phase of the field with respect to the clock that measures it. Two such tilts, close together, act like two angled arrivals stacked in the time coordinate, and the detector reads that as a redistribution of frequencies. In other words, Angle in space translates to frequency in time when you draw the picture carefully. All of this still respects the boundaries set by relativity. The front of the signal, the earliest distinguishable rise, never gets ahead of where it should be. The medium switch shapes what follows, not what begins. The group velocity of the pulse can be slowed, stopped, or made to appear to speed up through clever interactions. But the limit on information holds. The phase velocity can roam freely without moving a message. And because the time-slit experiment edits phase at specified instants, the natural domain where the interference shows up is frequency rather than screen position. With the photon as packet picture in mind, it becomes even easier to see why the packet's internal ripples are what set color. If you change the timing of how those ripples are sampled and reflected, you change which colors add and which cancel when they reach the detector. Now look at what happens if you change the angle at which those waves arrive. Picture a receiver that marks each crest of a light wave as it arrives. On a simple space-time chart, you draw a straight line for the beam and place small ticks on a black timeline every time the next peak reaches the detector. That is the calm case. Now, tilt the direction from which the wavefront arrives, so each crest slants differently across the time axis. The ticks crowd together, peaks register more often. In everyday language, the frequency has increased, and in visible light, a higher frequency means a shift toward blue. If you tilt the arrival the other way, the ticks spread apart, the frequency drops, and the light shifts toward red. The connection between frequency and color is direct, so the color changes make sense. What feels less simple is what this space-time drawing implies for how the light seems to travel. The straight, diagonal lines we began with represent the familiar vacuum speed, 299,792,458 meters per second. But once you sketch the angled arrivals that the time-slit experiment effectively creates, different segments of the path appear to take longer or shorter routes through the same space. Some stretches look as if the field lingers, arriving later than a straight-line vacuum path would suggest. Other stretches look as if the field leaps ahead and reaches a point before the straight path would allow. In the language of the diagram, parts of the history look subliminal, parts look superluminal, and a few slanted pieces even point in a way that, if you read them too literally, resembles motion backward along the time axis. It helps to keep the bookkeeping straight. In the time-slit setup, the sources on the left, drawn at two heights, are the same emitter at two different moments, and the receivers on the right are the same detector at two later moments. Nothing actually occupies two places at once. The experiment changes when the material reflects, not where. The lines are a compact way to show fields that are edited at distinct instants, then superposed at the detector. When you add those edited fields, you get an interference pattern in frequency, not a parade of photons that physically outrun the vacuum limit or turn around in time. The surprising geometry is a picture of phase relationships, not of couriers racing causality. Even so, the interference pattern carries a clear hint. To build the observed spectrum, the field must combine contributions that carry different phase histories. In a regular two-slit setup, those histories come from paths that go through two openings and arrive with different distances and angles. In the time-slit case, the histories come from two brief windows at different moments that stamp different phases on the same spatial path. When the detector sums those contributions, some frequencies cancel and others add, producing the comb-like pattern. You can describe this as light trying out multiple temporal routes, in the same modest way we say a wave in a pond tries out many paths when it diffracts around a post. It is not a plan. It is the sum over allowed ways the field can evolve, with the algebra selecting what survives. That language tempts a metaphor. Lightning branching through clouds, sending exploratory leaders into different directions before one channel connects and the main stroke follows. For light in these experiments, the feelers are phases, and the connection is an interference condition that sets which frequencies make it through. We never see a detector register photons from the future or messages carried faster than the front of a pulse. We see patterns that only make sense if the field's evolution is sensitive to more than one history, and if those histories are allowed to add and cancel in ways our classical instincts do not expect. The net effect is still grounded in the rules. The signal front respects the vacuum limit, and the pattern you measure respects causality, even when the sketch looks like a shortcut. This brings up a natural and persistent question. Can information travel backward in time? If it could, you could send a warning to your morning self or deliver tomorrow's lottery numbers to last week. Those pictures collapse into paradox quickly. In our macroscopic world, we never observe such loops. Time flows forward. Still, at the quantum scale, experiments keep showing correlations that arrive faster than our ordinary sense of cause than effect would suggest. It can look like influence that has no travel time or like coordination that happens outside the usual order. That is the strangeness that sits at the center of quantum mechanics. These effects do not grant an easy channel for faster-than-light messages or for time travel. They do, however, reveal that our simple, classical story about properties and causes needs refinement. One of the most striking demonstrations involves entanglement, a kind of linkage between particles created in a single interaction. When two particles are produced together, their measurable properties, like polarization, spin, or momentum, can be correlated in a precise way. If the total momentum of the pair is zero, then when you measure one particle's momentum and find it is left, you can infer that the other's is right, no matter how far apart they are. At first glance, this seems tame, like two friends agreeing in advance who pays for dinner and then sticking to the plan when they split up. That was the style of explanation Einstein hoped would save classical intuition. The particles carry hidden instructions from their shared past, and measurement simply reveals the values they already possessed. The trouble is that when people performed careful tests, the results did not match that picture. The correlations are stronger than any pre-agreed list of answers can explain. The statistics violate limits, Bell inequalities, that any local hidden variable model must obey. The quantum account says the pair is described by a joint state that does not assign definite, separate properties to each particle before measurement. Instead, the pair has a set of linked possibilities. When you measure one particle and get a result, the theory updates the joint description so that the other particle's corresponding property is now fixed in a matching way, even across great distance. No usable signal passes between the labs at that instant. You cannot choose the outcome you get on your side, so you cannot encode a message to be read on the other. But when you later compare notes, the patterns line up in ways that are impossible to simulate with classical instructions alone. This is where talk of backwards in time sometimes creeps in. In delayed choice experiments, scientists decide how to measure a particle after it has already passed a certain point in the apparatus. The observed outcomes depend on that late choice in ways that are consistent with quantum predictions. If you shoehorn the story into a classical timeline, first the particle chooses a path, then we choose a measurement, you end up saying odd things like, the future choice affected the particle's earlier behavior. A calmer reading is that quantum mechanics does not commit to a single classical history until a measurement context is fixed. The probabilities evolve forward in time, and the correlations are exposed when you make compatible measurements on both sides. There is no need to imagine a telegram to the past. The math governs how amplitudes add, not how messages travel. The distinction between influence and correlation matters. Entanglement can generate correlations that appear instantly across long distances, but it does not let you control outcomes to send a bit from one place to another at will. That is why there is no contradiction with the light speed limit. The front of a signal, the part that would carry a genuinely new instruction, still cannot outrun light in vacuum. Quantum mechanics gives you a different kind of resource: shared states whose joint behavior breaks classical bounds when tested side by side, later compared. It does not give you a lever to pull yesterday. If that sounds unsatisfying, it may help to look again at what we mean by having a property. In classical thinking, an object always has definite values for its measurable features, whether or not you check. In quantum thinking, a system can be in a superposition that assigns amplitudes to several possibilities at once. Measurement is the interaction that turns those amplitudes into a single registered result in your device. Before measurement, talking as if the particle already has one value or another can mislead. The more accurate statement is that it has a well-defined wave function that encodes the likelihoods for different outcomes. That is why, in everyday metaphors, people talk about questions like, if a tree falls in a forest and no one hears it, does it make a sound? In classical acoustics, the falling tree creates pressure waves whether or not an ear is nearby. In quantum language, at the level of single quanta, what counts as an event depends on interactions that register a result. According to quantum physics, not necessarily. Let's start with the experiment that pushed these questions out of philosophy and into the lab: Bell's test. The setup looks simple, the logic is not. John Stuart Bell asked whether particles carry hidden instructions that fix their answers in advance, or whether outcomes are created on the spot when you measure. He focused on a property called spin. Despite the name, quantum spin is not a tiny ball whirling. It is a built-in response to magnetic fields. You can test spin along any direction you choose. Along that direction, the result comes out in one of two ways, which we call up or down. Now imagine creating a pair of particles in a single event, so their total spin is 0. If, along some chosen direction, one is measured up, the other must be down to keep the total balanced. That is entanglement. The outcomes are linked. If you and a partner each measure one particle along the same direction, your results will always be opposite. That much does not decide between hidden instructions and made-on-the-spot answers, because both stories can reproduce that perfect anti-correlation when you happen to pick the same direction. Bell's clever move was to force the issue by having you and your partner choose measurement directions independently and at random from a small set. Keep the geometry plain. Picture 3 possible detector orientations, labeled 1, 2, and 3, evenly spaced. At each run, you pick one at random for particle A, your partner picks one at random for particle B, and you record whether each outcome is up or down. When the choices match both of you, choose 1, or both choose 2, or both choose 3. You always find opposite results, as guaranteed by the way the pair was prepared. The real test is when the choices differ. What fraction of those mismatched settings runs produce the same outcome, up, up, or down, down? and what fraction produce opposite outcomes, up, down, or down, up. Here is the fork. In a hidden instructions picture, each particle carries a pre-written answer for each of the 3 directions before you ever measure. You cannot see those answers in advance, but they are there. Because the 2 particles must be opposite along any direction, if you both measure the same one, their lists must be complementary. If particle A's hidden list says up at 1, down at 2, up at 3, then particle B's must say down at 1, up at 2, down at 3. When the settings you choose are different, you compare entries from different rows in those lists. If you map out all the pairings and count carefully, this class of models predicts a bound on how often your outcomes can match. In the simple 3-setting cartoon, you find that mismatched settings should agree more often than pure coin flip odds would allow. A typical bound is a match rate above 1/2. Different versions of Bell's inequality use different angles and give a precise algebraic cap. The spirit is the same. Local hidden instructions cannot reproduce certain patterns of correlation. Quantum mechanics makes a bolder prediction. It says the pair does not carry definite answers for all directions at once. Instead, the pair is in a joint state with linked possibilities. If both of you pick the same direction, the perfect opposite outcomes appear, as observed. If you pick different directions, the chance that your outcomes match depends on the angle between your settings in a way that cannot be simulated by any pre-written local lists. For some well-chosen angles, the quantum prediction for the correlation between results falls outside the hidden variable cap. With a 2-setting version known as CHSH, the classical cap is a number called 2. Quantum mechanics predicts up to 2 square root 2, which is bigger. Translate that back into match rates, and you get a statistical signature that no classical instruction set can fake. The beauty is that you can test this, create entangled pairs, separate them so that no light speed signal could sneak between the labs during a run. Choose your settings with independent random generators as late as you can. Record the outcomes. Repeat this many times. When analysts compare the data, the quantum pattern shows up. Experiments have been improving for decades, closing loopholes one by one, better detectors, space-like separation, cosmic randomness for settings, and the result is steady. Nature violates Bell inequalities. The correlations are stronger than any local hidden variable theory allows. That does not mean you can send a message faster than light. Each lab's individual outcomes still look like fair coin flips when viewed alone. You cannot force your detector to produce an up or a down at will, so you cannot encode a bit and have your partner read it out instantly. The unusual part lives in the joint statistics seen only after you later compare notes by ordinary communication. At that later stage, you discover that your strings of coin flip results line up with a pattern no local classical model can match. The non-locality is in the correlations, not in a usable signal. It helps to walk once more through the 3-detector cartoon to see how the numbers pull apart. Suppose a classical model assigns each particle hidden answers for settings 1, 2, and 3. There are 8 possible triplets of up and down, and for any assignment given to particle A, particle B must carry the opposite assignment entry by entry to enforce the always opposite rule when settings match. If you enumerate the 9 possible pairs of settings, A chooses 1, B chooses 1, A chooses 1, B chooses 2, and so on, then cross out the 3 same setting pairs. Because those are fixed opposite by construction, you are left with 6 mismatched cases. In this simple tally, at least 4 of those 6 will produce the same outcome under any hidden instruction assignment. That is a 2/3 match rate. Even if you broaden the angle choices and weightings, classical models keep their match probability above a certain bound. Quantum mechanics, by contrast, predicts a match fraction that drops below the classical floor at specific angles. The exact numbers depend on the geometry, but the key point is constant. Quantum predictions fall outside classical bounds, and experiments follow the quantum curve. The spooky feeling is natural. The moment you record up at your lab, the theory says the other particle's partner property is fixed to down for the same setting, even if the other lab is far away. It is tempting to say your result was sent instantly through space. That sentence overshoots. What you did was help choose which part of a shared, non-local description becomes actual when measured. No knob you can turn forces that choice into a message. When your partner looks only at their local data stream before comparing, they see no sign that anything happened to you at all. Only when both sides bring their logs together do the forbidden classical patterns reveal themselves. To see why this matters for time, add the twist that puzzled so many people: the delayed choice style of experiment. You and your partner wait until the particles are already on the way, or even until one has been detected before randomly choosing which property to measure or how to analyze the results. Quantum mechanics says the joint statistics will still line up with the final late choices. If you insist on a classical story that the particle already knew, a definite value for whichever setting you eventually pick, you will run into contradictions. If you try to save a classical story by saying the choice you make now reached back and flipped the particle's earlier property, you are smuggling retrocausality into your explanation. The calmer quantum reading is that the theory assigns amplitudes to possible outcomes that evolve forward in time, and only when the measurement context is finalized are definite outcomes drawn in a way that preserves the observed correlations. No signal to the past is needed, no faster-than-light instruction is sent. What is unusual is the joint structure of the outcomes across space and time. There is a clean way to separate faster than light from stronger than classical. The first would give you controllable influence. Set your switch here and force a chosen outcome there right now. That never happens. The second gives you non-classical correlations that defy any local hidden variable model when you compare data later. That is exactly what happens. When people say Bell tests disproved Einstein, what they mean is that a specific hope, local realism with hidden variables does not match nature. Relativity's speed limit for information is still intact. Quantum theory and relativity live together by assigning the weirdness to correlations without allowing messaging beyond light speed. One last practical detail makes the picture less abstract. In a typical modern Bell test, pairs of photons are created in a crystal, so their polarizations are entangled. Each photon flies to a distant station. Each station has a polarizer that can be quickly set to one of several angles by a random number generator. Behind each polarizer sits a detector that clicks transmit or reflect the two outcomes. The stations are separated so that during the tiny time window when a photon arrives and a setting is chosen, no light speed signal could travel between the stations. After many runs, the two lists of clicks are brought together. The correlation as a function of angle violates the classical bound and fits the quantum curve. Change the particles, change the distances, change the random sources, improve the detectors. The story repeats. The pattern does not depend on a clever trick. It is a property of the world. Where does this leave the idea of information going back in time? It leaves it as an interpretation, not a requirement. You can choose to tell a retrocausal story in which future measurement settings help determine past hidden variables. Some researchers explore that line in formal models. You can also choose to keep the arrow of cause pointing forward and let the non-local quantum state do the heavy lifting for correlations. Both pictures aim to account for the same data. Neither gives you a way to warn your past self about lunch. The data rule out local hidden instruction sets, but they do not open a channel to the past or a phone line faster than light. Still, the experiments matter for how we think. They show that properties are not always there, waiting to be revealed. They show that nature allows joint behaviors that no classical list of pre-written answers can match. They show that what you measure and when you decide to measure changes which questions make sense to ask about a system's past. And they set up the next puzzle cleanly. If we push the delayed choice idea one step further, choosing how to measure only after a particle would have had to decide its path. What exactly are we saying about the status of that path? The language gets tricky fast. The data stay simple. Record outcomes, compare them later, and watch the classical bounds break while the speed limit holds. There is a closely related setup called the delayed choice test. Its aim is simple to state and hard to shake off. If light sometimes looks like a wave and sometimes like a particle, when does it commit to either role? Classic double-slit experiments already showed both faces. With both slits open and no path check, the pattern on a screen builds up bright and dark bands that only a wave can explain, crest meeting crest, crest meeting trough. If you place detectors to learn which slit a photon used, the bands vanish and you get two simple piles, as if tiny pellets chose one opening or the other. The unsettling part is not the two outcomes. It's the dependency on whether you ask a which path question at all. The delayed choice idea nudges that unease one step further. What happens if you wait to choose how to measure until the photon is already inside the apparatus? One clean way to do this uses a Mach-Zehnder interferometer, 2 beam splitters, and 2 mirrors. Send a single photon into the first beam splitter. With 50/50 odds, it will be transmitted into path 1 or reflected into path 2. The two paths bounce off mirrors and meet again where a second beam splitter might be. Downstream sit 2 detectors. If both beam splitters are in place and the path lengths are tuned, the wave from path 1 and the wave from path 2 interfere, so that one detector always clicks and the other never does. That always never result is a crisp wave signature. The photon's probability amplitude went down both arms and combined with itself. Remove the second beam splitter and the story changes. Each path now points directly to a different detector. A click at the top detector means the photon came from path 1. A click at the side detector means path 2. There is no interference because you have made the paths distinguishable in principle. You do not need to build tiny cameras and watch the photon move. The geometry itself now carries which path information. 2 separate roads lead to 2 separate ends. Each photon triggers only one detector, and across many runs you get about half at each. Delayed choice puts the decision point after the photon has passed the first beam splitter. You let the photon enter, and only then, just before the 2 paths would meet, you either insert the second beam splitter or keep it out. In practice, an electro-optic device flips its state randomly at the last possible moment. If the second beam splitter is in, the outputs combine and the downstream clicks show the interference behavior. If the second beam splitter is out, The downstream clicks show the which path behavior. Run this many times with the choice made late and randomly, and you still see the same clean split. Interference whenever recombination is allowed, path knowledge whenever it is denied. The jolt comes from timing. It feels as if the photon should have made up its mind at the first beam splitter, either go left or go right, or split if it is a wave. But when you decide long after that first fork whether to allow the second recombination, the statistics follow your late choice. Insert the second splitter, and the pattern you collect requires the photon's amplitude to have explored both paths. Remove it, and the pattern requires the photon to have taken only one. The temptation is to say your later action reached back and told the photon what to do earlier. The calmer reading is that quantum mechanics never assigned a definite path in the first place when the setup made the paths indistinguishable. The measurement context, whether the two paths can interfere, determines which kind of question has a sensible answer. Until that context is fixed, talking as if the photon already had a classical path is like arguing over the color of a sound. It helps to lean on two linked ideas: complementarity and indistinguishability. Complementarity says certain questions exclude each other. If your apparatus is arranged to reveal which path the photon took, it is not arranged to let amplitudes from the two paths interfere. If it is arranged to let amplitudes interfere, it is not arranged to reveal which path. Indistinguishability is the technical way to say the paths are mixed so perfectly that no trace remains in the world that could, even in principle, tell them apart. In the recombined case, the second beam splitter and the matched lengths erase which path information. That is why interference appears. In the open case, the geometry preserves which path information. That is why interference disappears. The photon does not switch personalities in mid-flight. The laboratory decides whether path is a well-posed property at all. Variations underline the point. In quantum eraser versions, you first mark the paths in a way that would kill interference, say, by giving each path a different polarization, and then later erase the mark by projecting both polarizations into the same basis before detection. When you sort the data according to which erase setting you chose, interference fringes reappear within the sorted subsets, even though, taken all together, the full data show no fringes. The order of choices can be arranged so that the erase action happens after the photon has moved past the region where you think the interference would have happened. Nothing in the recorded clicks requires messages to travel backward. What the data require is that when the paths are made indistinguishable relative to the final measurement, the amplitudes add. When they are distinguishable, they do not. This is not wordplay about bookkeeping. It is about what counts as a physical alternative. In a classical picture, the photon is a tiny marble. It must have gone left or right, and the later gadget cannot change that history. In the quantum picture, the left and right alternatives are components of a single state. Whether those components can interfere depends on the whole arrangement, including elements you flip late. The wave function evolves forward in time, and your late choice changes how you decompose that state at the end. The probabilities you compute match the observed clicks. No detector ever registers a contradiction. You do not get a click at a place where, given the final arrangement, the theory says the probability is 0. The apparent retroactive flavor comes from insisting on assigning earlier classical properties in a situation where quantum mechanics tells you not to. A common worry is whether delayed choice smuggles in instant transmission of information. The experiments are engineered so that the late choice and the photon's arrival at the second station are space-like, separated too far apart in space and too close in time for a light-speed signal to connect them. You cannot use the setup as a faster-than-light communicator. The detector that records the photon's click has no way to know, from that click alone, whether the other device chose to insert or remove the second beam splitter. Only after you compare many runs do the statistics reveal which configuration was in place on each trial. In this sense, delayed choice is like Bell tests. The strange part lives in joint patterns, not in a single-shot steerable signal. If you prefer a story in space-time pictures, imagine drawing the photon's evolution as a broad line that forks and reunites. With the recombining element present, both forks feed the same output in a way that keeps track of relative phase. With it absent, each fork leads to its own detector. The broad line is a reminder that before detection, the quantum description does not say the particle is here. It says the amplitude to find it here evolves like this. When you recombine the forks coherently, the here from one path comes with a phase that can cancel or enhance the here from the other path. When you do not recombine, the paths never meet phase to phase. The world then presents you with two disjoint places where clicks can happen, and the clicks obey simple 50/50 odds. Nothing in that account forces you to abandon causality. What it does force is a retreat from the idea that particles carry definite answers to all possible questions all the time. That retreat began with Bell's theorem and continues with delayed choice and quantum eraser demonstrations. The patterns rule out models in which measurement only reveals pre-existing local properties. They do not hand you a device that can revise the past. They do not let you write a message to yesterday. They do suggest that the categories wave and particle and the categories path 1 and path 2 are not fixed labels you stick on a photon independent of context. They are roles the quantum state can play, set by how the world is arranged when you finally ask. There is room for interpretations here. Some researchers explore retrocausal models in which future boundary conditions help determine past events. Others keep causality pointing forward and accept that quantum states are non-local joint descriptions, not private inventories tucked into each particle. Still others lean on decoherence, which explains how fragile superpositions turn into robust classical-looking outcomes when systems interact with their environments. All of these frameworks agree on the laboratory facts. Set up a coherent recombination, and interference appears. Preserve which path information, and it does not. Make your choice late, and the statistics still follow the final arrangement. No run ever shows a photon both triggering a which path click and contributing to a fringe at the same time. No run ever shows a detector firing before its cause exists in the apparatus. The oddness sits in how possibilities are handled, not in messages sprinting into yesterday. If you want a guiding sentence to carry forward, use this. In quantum mechanics, outcomes are not assigned until a measurement context fixes what outcome means. And correlations can be stronger than any classical picture of pre-written answers allows, while still respecting the rule that information does not outrun light. Delayed choice experiments underline that lesson. They are not proof that light can see the future, and they are not evidence that the past can be edited at will. They are reminders that the questions we ask shape which properties become definite, and that the world's microstructure obeys rules that are precise, repeatable, and by the standards of everyday intuition, very strange.